Swayam Prabha. Digital India. Educated India.
So up to now we look to LTB of uniform members. We already had the stresses non-uniform. We saw that way to handle the non-uniform stresses on a uniform cross-section is done with the help of the CB factor. But if we have also, and even there we already saw, or at least I mentioned, that if you use the formulas, they will give you always an n critical, or in this case always an m critical value. But if you use a mathematical approach that gives a load multiplier, and actually if you want to calculate the m critical value, then you need to select a cross-section, take the bending moment there, and multiply it with the multiplier. But which cross-section really to select? It seems to be obvious to select the cross-section where there is the biggest bending moment. It's fine. But for example, if you know that there are maybe also other effects on the structure, it's not just pure bending, but maybe compression and bending together, why necessarily the moment of the biggest bending moment is the most interesting? Why not maybe the biggest compression, or maybe a sort of balanced combination of the two? So it's a bit foggy. That's why anyway, if we spoke about the fact that we are using a numerical determination of this critical something, the eigenvalue is a multiplier. The eigenvalue mechanically it basically means that we have a certain stress distribution, how much times we can increase that linearly along the structure to find the elastic buckling problem somewhere on the structure. We don't know exactly where, somewhere. But this is a multiplier, so the actual loading can be multiplied by this value to have a problem. So it's much more logical to reconsider the slenderness definition not as the cross-section strength divided by the critical force for compression, or the bending cross-section bending moment strength divided by the critical bending moment, but for something more general, which means that we use directly the load multipliers, the critical load multiplier. Anyway, this is what comes out from numerical solution. So let's try to create also a load multiplier for the other value under the square root. And if we start to use web tapered members, where even if we have a uniform bending moment on them, rarely, but we could have, even then the stresses are not uniform anymore because the cross-sections are different at each position. If we just, we will not make it together because we are running out of time. We just show it here, but we will see later on during the week how to define tapering and such. So this is now a slightly tapered version of the first example, uniform bending moment at the ends. So this is normally what you would assume that CB is equal to 1, but the cross-section, the element is web tapered, so that means that the height is changing from certain number to another certain number on its end. And if we want to calculate the slenderness of it, then by tradition we would need the critical moment, but what is the critical moment of this? It's a bit difficult to know. So that's why it's recommended not to use the critical moment anymore, but use the multiplier, which can be basically very easily created. All the MYC and the M critical moment we just write as a sort of formula, like the selected moment multiplied by something. And this way we have two values. In this case, in the papers which we made together, we call them as gamma because these are probably the most close to that AISC concept, which doesn't really exist officially. In Europe, these would be called as alpha. So in Europod, the upper value would be called as alpha ultimate, alpha ult. Lambda is your eigenvalue? Yeah. Okay. Yeah. Okay, but in Eurocode, the upper value would be alpha ultimate, alpha ult. This is a cross-section strength multiplier. How much time can I multiply my load to cause cross-section strength issue on my structure? And the bottom one is called as alpha CR, alpha critical. That's the multiplier of the actual stress distribution to find elastic buckling somewhere on the structure. But based on more close to the concept of the naming convention of AISC, we decided that we will try to use them as gammas. I tell you in advance that in Consteel, sometimes you may still find not these, but the European type of thing. So these are those confusions that I said at the beginning. Our focus was on trying to bring results and not necessarily all these additional things. Okay, so and if we go into this definition of the slenderness for LTB, we speak about LTB only, then the gamma E LTB is the value which comes directly out as the eigenvalue from Consteel or from any other software. If we use just compression, 6-degree freedom Beam is fine, so that value, but ETAPS or others would give that is the alpha critical, and we just need to calculate the other value, and the other value is just calculated as the ratio of the selected cross sections bending moment strength divided by the actual internal force bending moment in that cross section. Now this picture went a bit bad, but so if we would try to follow the approach defined in the design guide 25 for this, the first of all I didn't do because I'm unable to do, sorry, it's so difficult. But okay, sorry, I should have done it, but I didn't do. Okay, but anyway, so it's I just gave here the different formulas to do that. So first of all, as I said, even in this case, the CB is not 1 anymore because the bending moment diagram is uniform, but the stresses in the compression flange are not uniform. There is a stress gradient, and that stress gradient should taken into account. So a different than 1 value can be obtained. Actually, it will be probably bigger than 1. So it's in that case it's on safe side to neglect it. And it's always safe side to use CB equal 1. But so one could use a CB bigger than 1 even if this is a uniform major axis bending situation. And then the calculation would in addition, further complicated by the fact what Professor White has mentioned, that if we have slender web, then by AISC we should consider the torsion inertia as 0. It's again an interesting question because the way how it is written in the code, I think, is that if within an unbraced length you find at least one position where certain condition is not fulfilled, then for the full unbraced length, you must consider this equal to 0. Now, it's fine if you know what is the unbraced length. But as I said at the beginning, very often you don't really know what is the unbraced. You as a human, you may say that, maybe here or maybe there. But it's not always clear where is the end and where is the start of it, because even that is important. If you just 200 millimeter more left to the right is the start. So at the moment, we implemented this thing in Consteel, but in a bit this way, we consider this condition for those finite elements where this condition is fulfilled. So if a finite element is slender, then on that specific finite element we take equals 0, but not on the whole unbraced length, because unfortunately we don't know how long is the actual unbraced length. Okay, but that's our problem. If you follow the hand calculation, it was given in the design guide 25 that you are supposed to know what is the unbraced length. And then again, the idea is that you need to find a key cross-section, and that key cross-section is where the required compression flange from major axis bending stress to the elastic stress ratio is the biggest or is the maximum. So you need to scan through your structure, find the cross-section which is the most exposed to the bending moment, and then you say that is your key cross-section for the further calculation.
Again, what he's talking about here are all to support hand calculation.
Yeah, this is for supporting the hand calculation. Now, this is not exactly what Consteel does, but actually a very similar thing is done by Consteel behind the scenes. So if we do the calculation with Consteel, that's very easy. We just make it tapered. There is a functionality to make it tapered, and we run the calculation as we saw. And without hesitation, there will be a number. There will be always a number. So it always comes out a number. And this number will be obviously different from the situation of being uniform. But then how to make then the calculation? And for this, I cannot really show well. But what Consteel is doing is exactly the same, that we will find the critical cross-section, which is the most utilized in function of the actual stress distribution from the bending moment. So that means that we scan through all the cross-sections on the member. What is a member is something that you define. So you have certain control of what is the member, but this is member and this is not embrace length. So these two things could be the same as well, but normally we define as member as the whole height of the column. So that probably is made of several embrace lengths. So the full height of the column, we scan through all the cross-sections. We find the cross-section which gives the highest cross-section utilization. If something is, for example, this is actually very complicated, especially if you have a web taper member. Some parts, the web is still full effective. Then due to the web slenderness starts to be effective, then you need to calculate the effective width on the column, and then you go further away, it will be more and more and more slender. Suddenly, web thickness can change from 4 millimeter to 5 or to 6. Web flange can change, so it's quite a heavy thing. So we scan through all the cross sections on the member to find that for the actual load combination, which is the most critical purely from cross-section utilization point of view. And then on that specific point, we calculate this gamma SG value, which I have shown here, this gamma SG. So the gamma ELT becomes automatically again, by calculating easy, nothing to do with that. But in order to calculate this upper value, we need to do quite a heavy exercise to find by scanning all the profiles of the cross-section. And then that will be that specific key or reference point. Basically, it's a transformation of the taper member into an equivalent member with a uniform cross-section. We have no direct solution. Again, so as it was also questioned here during the break, Consteel is everything what we said is elasticity. So there is no inelasticity here. So this is purely elastic, no science, no big science. So elastic calculation, and of course the reality is inelasticity. So the real strength, we cannot base the strength calculation on elastic results. What gives the link between the two are the buckling curves. The Eurocode or AISC or Indian standard buckling curve is responsible to provide the link between the elastic slenderness and the strength. So every effect of residual stress and every other thing are supposed to be in the buckling curve. Of course, this is complicated if we have members, adjacent members. That is only considering the member an isolated member. So those things internal is fine, but once one member has an impact, it yields, and because of that, its stiffness gets lower. Therefore, its stabilization or rotational impact on the neighbor becomes suddenly less. That's not something what the design standard. So the buckling curve doesn't know that. So it has limited possibility, but so the link between elastically calculated slenderness and real strength is provided by the design standard. In the design standard, this equivalence is only given for uniform members. There is nothing for a web taper member. So that's why first we need to make a transformation of the web taper member into an equivalent uniform, and this is the way to make it. So find the cross-section which has the same cross-section thing, and then consider that cross-section, and for the critical value we really have the value which really corresponds. That's the more precise value, the critical multiplier, because that's really the structure as it is with its real stress distribution. That is very precise. The upper value is an approximation, but this is the transformation into a uniform member. And again, from here, the buckling curves are used to really predict the inelastic strength.
This is what we were talking about with the columns later, I guess on Friday last week, and he's taking it the next step here too. How do we address the flexion?
Yeah. So basically, just a summarize of things that M critical load multiplier. If we have pure compression and the cross section is uniform, of course, then the stresses will be also uniform. Then there's no problem to use the n critical value. It's a very easy to be defined. There are formulas, everything. We can use the n critical as a value to come to the non-dimensional slenderness, lambda n, or I don't know how you called it in the beginning. And once we know the lambda for compression, then going to the buckling curves for compression. In AISE, this is the one which is made of two parts, the Euler-like part and the other exponential part. Doesn't matter. We read the reduction factor based on the slenderness, and then we calculate the strengths, and it doesn't matter at this context at which point we take for the py, because all are the same. Absolutely analogically, if we look to pure major axis bending, then again we can use the m critical value for which there are closed formulas and such. We can calculate based on this advice, which is new to AISE, is not found in the existing 2016 edition, 2022 edition. 2022 edition is still based on LB. Okay, so this is not in the code. It will come in the next edition, or it's already in the design guide 25. But you can come directly based on analogy to the reduction factor, and then you can do the same game. Again, doesn't matter which cross-section you take, because all are the same. Immediately when we go to the domain of non-uniform sections or non-uniform stresses, it is not recommended anymore to try to pick an n critical or m critical value, because it has less and less meaning. So it starts to be more and more artificial to try to stick to it. It's much easier to go into a way of generalization, introduce the concept of load multipliers, basically just change the actual values into load multipliers. And what is important, that for this game we need to select one cross-section which will be the reference cross-section. For that, there are certain recommendations. Our recommendation is that in case we have a pure compression problem, then now I wrote on the inverse, but doesn't matter. So find the cross-section which gives the highest utilization, cross-section utilization regarding compression, and that's the value of the multiplier for the slenderness, and then the rest is the same. But we calculate the member strength in this single point only. So we don't need to calculate it at every point. We find the point, and we assume that the equivalent column has that cross-section, and from this point of view, it's already uniform, so it doesn't matter which cross-section we take. We always take this artificial cross-section. And if we have a pure bending moment problem, that's fully analogically the same. Just the way how we calculate this gamma as G related to bending moment is obviously using the bending moment type of things. Okay? And this will be the moment when we go further to the real general method, which basically means that even this separation is not needed. So we don't need to try to calculate the flexural buckling resistance, assuming that there is no moment, although we know that there is, and then try to calculate the LTB strength of the member, assuming that there is no flexural buckling, although there is. So to have two artificially clean results, and then try to combine them into, I saw that Indian standard uses the same interaction formula as the Eurocode, the Annex B. Eurocode has two, a French, Belgian, and a German approach. It seems that you took the German, but those are terribly complicated, both. So I don't know who can really calculate those. So it's very difficult to calculate them. And again, those are only for uniform members. So if you have a web taper member, you can start the game. Many people don't even, that's very disappointing. Many people don't even realize, and they use it. Or other trick is, they say that they cut the element into short elements of uniform. But that's wrong. That's, of course, that's better than nothing. But that's wrong. That's not the intention. Eurocode, from this point of view, is clean. Eurocode says if you have to do something more than use the general method. But the problem is that also the Indian standard hasn't implemented the general method, so you have now a big gap. But the gap is probably not very much visible, because people, I think, don't realize that there is a gap, because they do what they can do, of course. Uniform, okay, then take the average cross-section or the 2/3 of the biggest. I don't know, there are many ways how to try to invent this equivalency, but unfortunately that's not true. Those formulas are heavily calibrated really by test results, so there is no mathematics behind. The mathematics was just the basic. After that, all those, maybe they look like as contain some lambdas and others in the formula, so you may have the feeling that that came out from a differential equation. No, it's just numerical calibration presented in a way which seems to be more familiar to an engineer, but it's nothing. And the problem is that if you try to use it for something else, it will be just wrong. How wrong, you never know, because you have no other value to compare with. So this will be your best guess. But you never know that is it good or not. But it's clearly written that it's only for uniform members with uniform cross-section. Okay? And now when we start to speak about the general method, is simply that's basically another step toward generalization. Again, even more heavier, assuming that you have a computer tool which can calculate the stresses, because basically it only says that we don't need to make this separation of norm to try to calculate the gamma A, F, B, assuming that there is no. Even the whole thing is very simple. Imagine if it's just simplest thing, you have a porta frame, okay? And you try to calculate numerically the load multipliers. How the hell you can create a stress distribution structure which has no any bending moment impact? You put the load on it, and every cross section you will have normal force and bending moment. So if you want to calculate, you just simply go into the stiffness matrix before you populate the geometric stiffness matrix. That every stress which you believe comes from bending moment, you make it into zero. Is that really, does it make any sense? There will be no even equilibrium at the connected members. So this is artificially separating one from another. If you speak about isolated members, well, it's probably fine, because isolation means there's no continuity. So this problem disappears automatically. But if you try to keep it together, it makes no sense. So formally, you can force yourself to try to calculate these values on a structural level, but probably it really makes no sense. It is just to try to fulfill something written by others. And actually, there's really no need, because this value you can easily calculate without the separation. Much easier to calculate without separation than try to do a separation. The problem is, again, what is with the higher value there. But again, Eurocode for this made something extremely simply, interpolation. So there is nothing more than just, again, that's the best can be done. Of course, very complicated things can also be created, and probably should be. It's very important, the general method of the Eurocode, and that's what we also recommend to be also implemented in this AISC context. Actually, it's a very simple approach, and this is probably conservative. So if you are able to create a very, very perfect interaction formula, hopefully that gives more realistic and higher strength. If not, then it's disappointing, because with a lot of work, you create something which is less beneficial. So this is an approximation. It's safe side, but it can be automated. It can work flawlessly for everything. So basically, it means that we are generalizing the slenderness values. We will not have any more lambda n and lambda lt. We will have one common slenderness. That slenderness is calculated from a generalized cross-section utilization and from the load multiplier, calculated without this artificial separation into compression and bending. We have just one slenderness, and after that we go into different words. From the slenderness, from this common slenderness, we read one value on the column curve for the He value for the flexural buckling, because we still need that. So the NRD, or no, PN, or how is it called, the flexural strength of the column is still calculated formally the same way, He times N, but the He is not calculated from this artificially separated slenderness, but from the commonly calculated slenderness. And also for the He LT for the lateral torsional buckling is calculated from exactly the same slenderness. So not two different slenderness values are found, but just one. This is basically an equivalent slenderness. Somehow average of the two. It's not a mathematical average, of course, it's not that simple to do, but basically something which contains the effect. If we have a column where compression dominates the situation, that this combined slenderness will be very close to the separately just for compression calculated slenderness. But it will be slightly different as much as additionally the bending moment has an effect. If the bending moment is the dominant effect and compression is nothing, then this value will be exactly equal or very close to the one you would calculate for the lambda. And if you have something in between that, this is a value in between. A value what you cannot calculate. There are no formulas for that because it depends on the ratio of the compression to bending moment. So there are no formulas ever created for that. But numerically, it can be calculated. And after that, what we say that we still calculate a compression strength and the bending moment strength, and we just use the very well-known interaction formula. There is no need for any more calibrated values because, especially if you go to the Eurocode concept or to the Indian standard, you don't use that complicated interaction formula which has those many K, Z, Y, K, Y, Y, K, I don't know how many different CM, LT, CM, Y, many other things. No, that's not needed because basically that calibration, most of the reason why the calibration is there is to try to involve into the formulas some sort of second order effects, some sort of other things, but partially can be captured by this calculation anyway. So it's a possibility to consider exactly with the same approach the combined situation as it was presented separately for compression and for LTB. And this combined situation is a very robust and can be really automated in a software to perform calculation. What is important that this is only for the out-of-plane direction. So here we take this for LTB and for out-of-plane buckling. This cannot solve the problems of global sway type of things. So that's why the recommendation is based on the Eurocode is that the calculation has two legs. One, for the traditional, the in-plane calculation, Eurocode requires, and also based on our recommendation, we must use imperfections, global imperfections on the structure, and perform a geometrically nonlinear but materially elastic calculation. This equivalent geometric imperfection considers all the required imperfections to cover the in-plane related buckling problems. And then in addition, perform the general method to make sure that all the elements of the structure have enough strength compared to the actual demand. And this is, and then we will see later, because that's still not enough. This will be fine for an independent member, because we will come to the problem what we already touched, that one buckling mode probably refers to the weakest part of the structure and not to every member of the structure. If we as a designer, we are not trying to judge if a structure is good or not, needs to be demolished or can be kept, but we are designing a structure, then we try to make every structural member optimally designed. So it's not enough to just say that the structure is good or not good, but we need to really see that we need this information for every member, if they are good or not good, if they are over-designed or under-designed. And for this, we will see that the use of the first only buckling mode is not enough. The first only buckling mode probably refers to the weakest part of the structure, unless this is super properly designed for a full homogeneous effect, which is impossible. If you have a normal structure, there will be always elements which are stronger than needed due to many other reasons, maybe due to deflection criteria, so maybe there is no 8 millimeter deep hot rod eye section produced because it's impossible to produce such a small one, and you will use at least 100 millimeter deep, or you just cannot buy it in the shop and you will use a deeper one, or you have it from the previous project left some profiles and you want to use them. So it's impossible to have everything homogeneously designed, and therefore the general method itself must be further supported with some functionalities to really finally come to that goal that it can really be an automated design. Especially if we speak about meta buildings. Meta buildings are very easy structurally. Typically they have mainframes, which are really 2D structures. They are laterally supported at certain position by structure elements which are mostly secondary components or some additional bracing pipes or I don't know what, or crane beams. Crane beams are very often not considered because maybe that can be removed later on, and then what about the bracing? So, but again, it's the decision of the engineer. But structurally, these are relatively easy. It's very easy to distinguish in plane and out of plane. Usually, no one has the crazy idea to rotate the I section by 90 degrees. That's where typically the problem starts. If you have a structure where everything is rotated like that. According to Eurocode, Eurocode always assumes that it is it can be defined in plane and out of plane. This is not always true. You can create a structure where you, like also Professor White has shown an exercise where they are just, his students are working on it. Just imagine a table with 4 legs, and all legs are rotated in the opposite direction. So there's no, each are rotated like this. So you cannot create a frame section. What is in plane? In plane to the structure or in plane to the column? So there are such tricky things, but at least for a meta building, the life is easy. Typically, there are frames, porta frames, where every profile stands in a way that it makes sense. No one has the idea to rotate. So for the in-plane, we can easily apply imperfection. Easily. Even that is not easy, how to apply imperfection for a porta frame, because I think even that is not well defined, especially if the porta frame has a web-tapered member. So that's already a certain complication, but it's relatively solvable. And regarding all the out-of-plane buckling phenomenon, the general method can be used as a perfect solution, extended with other things which we will cover on how to make sure that you assign to certain members of the structure really the first eigenmode or maybe a higher mode, because there are many others. As we saw, the computer can calculate also higher modes, and there is a certain feeling that why not use the others if there are also similar things, and they would give another critical stress value. Maybe those are more appropriate for other members of the structure. So the general method is an interpolation solution. It makes the continuity between the pure normal force and pure bending moment situation. It heavily builds on the fact that we can perform numeric calculation of the critical eigenvalues, elastic. So no separation of n and m, but everything together. The method itself, based on the Eurocode, is the only method which can be used for out-of-plane buckling of any sort of structures, which may have non-uniform members or any sort of effects, because the interaction formulas for n plus m, they are only for uniform members. And most probably, not most probably, but clearly, those are calibrated for hot rod members. So if somebody has welded sections, then at least most of, no, there are some formulas, there are some different tables, I think, for hot rod and welded for those, but probably most of effort was made for the hot rod, because that's the most interesting economically and scientifically, or at least sponsored by the industry. In Europe for sure, yeah. But I think also in your country.
Manufacturers will tell you they can manufacture.
Yeah, for sure. But if you look to how big proportion of the steel profiles are used for meta building and for the traditional, then traditional, I guess, it's 90%. No. So I think the traditional steelwork, they use the W profiles. No, so with this general method, so we will see now starting from tomorrow, but maybe we can start today. When we need to finish at 6?
I think probably it's good to wrap up today.
Yeah, yeah. So what we will continue to go now to go into this general method and see with examples. This is really an interesting opportunity to to cover nicely those things which are basically unsolvable, or no, nothing is unsolvable. Of course, Eiffel Tower was designed, I don't know, 200 years ago, and all those beautiful steel structures are built on the world, and of course they were designed by engineers, so it would be stupid to say that they are not designable. Of course they are designable, but there are a lot of unclear things. If when the general method is used, many things are much clean, and if an engineer if adopts this approach, then that's what we always see when we manage to convince somebody to use Consteel, that they suddenly feel that they have bigger freedom to try different structural configurations, because very often an engineer who is educated enough to know the stability problem will not select solutions for which he cannot calculate the appropriate values. And he will immediately drive his way of thinking to those type of solutions for which he will be able to really solve it. Of course, young engineers, maybe they who know nothing, they will be open-minded and they try everything, but there is no guarantee that the result will be correct. Older people with bigger experience will probably realize that it's not funny to try to invent new things and then have big problem later on that they cannot really assess these values. So with this approach, again, this freedom of creating everything is back to the hand, because you don't need to define these. You just create a structure. If you try to make something as a truss, as a porta frame, as put some additional columns to every sort of thing, you can stabilize it. You can put into your model really those flange braces which are in a metal building, and they will really do the stabilization by themselves. So you can put any type of structural element in the model, and they will really play the role what you expect. Typically, when we design structures, there is a huge difference between the calculation model and the structural and the Tekla model. The calculation model is full of simplifications. I'm not speaking about Abacus and others. Abacus, of course, that's super reality for one element. But for an engineer, the calculation model, typically everything is somehow compressed into one straight line. Member eccentricities are hidden, are shifted, pushed into the same plane because it's difficult to consider it, or anyway the software cannot do. And then they make some additional tricks to, if they don't forget, they put some additional delta moments by hand into the calculation, which doesn't come out of the software. But there's a lot of such simplification because you cannot. Now, if you work with Consteel, there is a chance that you try to model everything as it is. You don't make these traditional simplifications because Consteel can take these into account. And plus, you even have to do a model as precise as possible, because you never know what impact this simplification might have on your critical stress level, and you are not in the position to define K values. So if you had a good way to work on the traditional way and really believe that you always knew the correct K values for all these things, then it's a problem that if you make a simplified model and you expect to have good results from Consteel, because Consteel will not be able to give good results because it will always believe that the simplified model is the reality. And if that leads to different critical stresses, then you will get these wrong critical stresses, and in addition, you have no chance to define your very well-known K values. But if you are ready to build a structure much close to reality, as again, today everybody speaks about beam and transfer between softwares. We import the model from Tekla or from Revit or from other modeling softwares. People, when I was young, then a building was just designed in 2D. So one middle frame was designed and said it's 10 times more. Now I see even the simplest building, if everything is the same, they are all in the model. Why? Somehow that's the feeling of the modern engineers, that they need to do everything as it is because 3D, because of I don't know what. So anyway, there is a certain tendency. Computers are stronger and stronger, so it's more and more feasible to do. You need to do collision check, beam, all these things. Somehow a certain workflow is assumed. Of course, if you design just one and repeat by 5, that's difficult to tell to the computer. It's much easier to design, have all 5 in your model, and then everything is designed. So with this general method, and especially for such metal buildings, where there's a very clean load path on the buildings, we see that this is a very good possibility to design with buildings. Consider the fact that they are full of non-standard solutions, web-tapered members. Often you can have just a purlin without these flange braces, so that means that one flange is supported laterally, but the other not. Of course, maybe it's a good idea to put everywhere a second, but maybe it's not possible, or maybe it was not done, and you need to verify a structure which has been built without these everywhere, and then you need to say something about that. So there are many situations when there is no fork support. You have not uniform members, there are no fork supports. You want to consider the effect of we will see later. As I said, the AISC typically gives you bracing, stiffness, and other stiffness requirements. If you fulfill them, then you can simplify your model. If you don't fulfill them, then it's foggy if you can do anything or not. Very often it happens with these buildings that they cannot fulfill these rotational stiffness requirements. As I said, I spoke with some people of the metal building industry in the United States, and they said that, for example, if they have this floating roof, I guess it's also used in Indian metal buildings, that there are not screws are used to fix the panel to the sheeting, especially due to the huge thermal expansions that you may have here. It's important to find such solutions when the thermal expansion of the roof is not transmitted immediately to the supporting structure. So there are such sliding connectors in these roofs. And also, on the other hand, they are nicely watertightly seamed together as a big continuity. But of course, there is a problem that they don't have, or very limited shear stiffness. They are not diaphragms. And if they really, all together as a system, can satisfy those quite strict stiffness requirements which are given in AIS3 appendix, I don't know, ABC? 6? There's no clear, and if those requirements cannot be satisfied, then it's not clear if there is still a solution to continue, or you must strengthen something to come back again to the track of well-known thing. With this approach, basically everything can be designed. Every sort of non-zero stiffness can be taken into account. Everything will then impact on the results, and everything will completely change. And based on a long years of experience, at least in Europe with Eurocode, this works. So many structures were designed in the last 25 years. Consteel exists since 25 years. And up to now, it was a European-only software, because of the fact that this general method exists only in the Eurocode since long time. We are not just a software developer company, but we are also representing Hungary in the different Eurocode committees. How is it called? I forget what is the name of the standardization institute, and also in ECCS, which is probably ECCS. This is a European Convention for Construction and Steelwork, or something like that. That's one of the main body behind the CEN. No, CEN is the Eurocode creation body, but mainly ECCS is the technical background committee or such. So we are representing Hungary in these committees. Plus, this whole general method is a creature of a German university in Aachen. There was a person who has died already. He was called, I don't know what is his first name, but his last name was Sedlacek. He was a very famous professor in Germany. Basically, he was the creator of this general method. And this general method is developed together with this Aachen University and by us here in Hungary. And plus also some people in Portugal, in Coimbra. And we are now working on a ECCS publication on the second generation of the general method. Because this present general method is very nice, very good, but there are still a lot of unsolved things and can be and should also be further improved. Okay, but it's already quite interesting possibility even today. And what we saw is that it works quite well based on the examples we checked up to now with AISC. And for my very big surprise, I was not aware, but the Indian standard is very close to the Eurocode. I didn't know that before I came here. So actually, even if it's not included in the Indian standard, mentally or conceptually it fully fits. Especially that you have exactly the same interaction formula, which is exactly by the same reason not applicable for a web table member. The solution by the Eurocode for this is the general method, and that is just clearly missing from the Indian standard, which was by any reason not considered for implementation. But basically, it is exactly as correct by the Indian standard as by the Eurocode. It's not necessarily the case by the AISC, because that has a different concept, but we believe that it's also applicable for that